continue with our program, we would like to invite Dr. Marcela Peña, who is an academic of the School of Psychology of the Catholic University of Chile, whose conference is entitled Bridges Between Neurosciences and Education. Her research work has centered on the study of human cognition from newlyborns to adults. Her topics currently underway discuss the neurocognitive basis of language, social cognition, logical mathematical thought, thinking and symbolic thinking, and human communication. Dr. Peña, if you may. Good morning. Good morning. I would like to thank Christian Rojas for inviting me and Gemelita Carrasco, who was the one who introduced me to Christian Rojas, and that's how I was invited to the seminar. I think this is relevant for different purposes, but if we consider that there is a way in which science research, not the precisely neuroscience research, could help such a noble task as education is, I think that's marvelous. I think a lot of what I will be sharing with you has to do with the hope of those who do science to be able to contribute to society in a highly relevant activity for the quality of life, which is education. I will be speaking little about the research that we do, at least that we focus on children before the first year of life, but I will share with you some of the findings we have arrived at in other domains, and we'll also try to have a discussion and reflection on how these scientific findings can impact education. Therefore, I will begin my presentation. My presentation will have the following structure. First, we will be talking about the title, which is in Bridges Between Neurosciences and Education. We'll be speaking about neuroscience and the complexity of the central nervous system, and we'll talk about the empirical data versus the application in the classroom. We'll talk about some examples. We'll talk about the critical periods of some events that have to do with why we should intervene and when it is useful for neuroscience to intervene, and how neuroscience can explain what those interventions, when they should be carried out, and sensory experience and other neural models, and then conclusions. This is more or less the script of my presentation. First of all, I would like to speak of the fact that neuroscience tries to measure in the brain the events that occur in the mind and behavior, and none of these domains or levels of representation of the child, what the child is thinking, are equivalent. The brain, when we do neuroscience, we add measurements as to how the brain responds, how much oxygen it consumes, how much sugar, and what are the metabolical components that modify brain activity and the consumption of different elements. We interpret those changes as a reflex of an activity that occurs at the behavioral level that we can all observe. If I tell the children to ask the child to say words that begin with P, and they say papa, that has to do with behavior. And at the mind, that cannot be measured. No one measures it. It cannot be measured. Maybe some people will disagree with me, but the mind is something that can be inferred. Adults can more or less speak about what the mind is. We all know what it is, but it cannot be measured effectively in accurate and qualitative and quantitative terms as we can measure the consumption of energy in the brain. The possibility to measure the brain by different metrics that are accurate provide a window of exploration for behavior and the mind. That would be neuroscience. Neuroscience tries, through the metrics of the central nervous system, tries to create a correlation between behavior and the mind, and in this case, learning, which has to do with education. Now, is that worthwhile? Is it useful? Yes, it does. At least in medicine, we can explain cases such as this one in which the most of the brain was missing. It was full of fluid, but this man could talk and walk, and he worked, he had children, he married. So that this allows us to understand the characteristics of the clinical syndromes, and then we can see what the brain says about these kind of phenomena. We can see also changes in economy, and we can also address that. But in education, I can say that this is not so clear. There's a lot of discussion regarding the fact that neuroscience is very limited, and it can not provide enough evidence for education. And this is based on something that I will repeat at the end that has to do with myth. There's a lot of myths going on about the brain, and that the brain will provide a great solution for such a complex problem as education is. So it is useful, but how do we transfer that to education? Well, we have some good examples and some questioning of those examples. I will say that practically everything I will share with you today are the good examples, because I think that I'm a believer. I think that neuroscience can be used for education, and in each of those examples there will be somebody revising them and questioning them and restricting them, and who do not accept that these findings are valid to explain any situation. Therefore, the ideal of cognitive science or neuroscience, cognitive neuroscience, is for us to be able to explain a phenomenon, for instance, in learning, in math skills or bilingual skills, and how the system, the nervous system is organized. It's organized at a molecular level. If we talk about neurons, and there we have the involvement of genes and the elements that are found inside cells. Then we have synapses and neurons. Neurons come together, they create a network tissues, and then they have regions and circuits. And these are underlie the behavioral and activities, and that has a cultural interpretation in education. What we do with this relationship between neuroscience and education is to try to see the levels of organization of the central nervous system and how this influences education and culture. Well, this is a review performed by Paul Howard Jones, and it says that the empirical data are more based on lab results, and some of them have been applied to the classroom, and that neuroscience can give us information as regards, for instance, how children learn math. And there's evidence that based on neuroscience as to how the central nervous system works specifically, how it can explain how anxiety affects performance in math learning, and how to just make approximate calculations rather than accurate calculations is beneficial for numerical cognition. And using fingers to count, for instance, if we train them to be able to have a very accurate representation of their fingers, how that can benefit math cognition and mental rotation too, which without a doubt is very much related to this capacity, and it's a very good predictor cognitively of the success of the STEM type of degrees like engineering and mathematics that have this kind of requirement for this kind of calculation and spatial type of cognition. And the case of reading, there's vast evidence that reading is represented in the brain, and I will provide an example later on about this. There are other elements such as aerobics, because of the consumption of oxygen and the increase of oxygen levels in the brain, sleep, nutrition, executive functions, critical periods, genetics. There are genes that could be related to the learning of certain skills, stimulation, and this requires interventions. What if I am not that good at math? And there's some papers and research that has been done by Bangladesh where they do electrical stimulation of the parietal parts of the brain in people who have problems with math calculations, and they find that they improve in their management of numbers and simple at a simple level. And also gestures help mathematical cognition, and this that shows that there's a spatial representation of the body, and then video games and neurofeedback. In all of these activities, there have been studies that show that there's an advantage of training or the practice of certain habits, for instance, eating habits or the choice of certain diet items that could improve learning, and some more than others, because there's a various array of them, have a great support from neuroscience. In some cases, there's poor evidence, for instance, the effect of video games specifically on education and learning is still quite recent for us to have a model as to how the brain could give us information about how the video games impact the plasticity of the brain. I would proceed to give you examples of what is in red. We will be talking about this from a perspective of our lab. To tell you a bit what we do at the lab as regards eating habits and eating, I will just go over this very quickly. I can't tell you everything that is known about this, but something that is critical is that the consumption of calories, of enough calories, particularly breakfast, has a great impact on the performance of children at school. And this has been documented and has been used to assess the way the brain reacts when it has to pay attention, just as Rosaria mentioned earlier in her presentation, as to why and how important attention is, and how that improves learning based on some models. Patricia Kuhl has a model like that one, and in fact, there are some good eating habits that have to do with the consumption of calories. Some of them, for instance, if we consume omega 3 and certain nutrients and vitamins that can facilitate and help learning so that the system becomes much more efficient, the nutraceutic type of systems. And here we have a study of the nutraceutical elements that has been performed on animals, and which could have an impact on whether we learn or we do not learn. For instance, here we see that the hemoglobin levels favor children who are performing math tasks and they improve their scores in math. The children with higher levels of hemoglobin do better. There's a direct correlation with their performance in math. Something that's also important, and this is quite controversial, is that there are certain diets that are noxious, that are not good. Just as there would be some diets that favor learning or the conditions of learning, there would be some diets that are harmful for learning. For instance, the ones that promote obesity. Their obesity is an issue, and as you may have well heard, in the future, obese children do not learn that well. One of the consequences of obesity is that the cognitive levels are affected and they are lower. And in animal models, we have seen the following, that high-fat diets desensitize the NMDA receptors that have to do a lot with learning. So we must improve children's diets and try to increase the factors that help them learn. This could help us decrease the levels of obesity or the high intake levels of fat. And also aerobic exercise In this case, there is evidence that it improves the neurotrophic and neurogenesis of the brain. It increases the oxygen levels locally, and that helps the brain have higher oxygen levels. In addition to that, there would be some other relevant factors at the neurotransmitter levels that would facilitate the development of skills for learning. However, there's a study that I have placed right here by Valerie Carson, who has done a systematic review of the effect of physical activity and aerobic exercise on the brain. And the truth is that she concluded after several trials, because this is one of the reviews in 2015, but she's also performed a study in 2014. What she says is that we cannot be sure yet fully that the physical exercise is the panacea and that all children must exercise, otherwise it would be lost. But in fact, there are situations in which aerobic exercise helps, and there's a vast amount of data showing that. But there are other studies that show that physical activity does not influence the cognitive skills of children, at least during school age. This is another one. What about sleeping? This is something that, is just old truths, old known facts that if you sleep well, you will do well. As our grandmothers would recommend to do. So that's why we have to bring science into this. Science does not work only on the basis of intuitions. We must have empirical evidence through experimental methods to be able to assert what we are saying and to find the limits to what we are asserting. In this case, sleep. There's some spindles that are called sleep spindles. It's electrical behavior or activity in the brain, and it shows you what happens in midday naps. Do preschool children nap or not? Who believes that they should nap? And who's against naps in young children? Good. Well, in fact, this is a study that is against. It says that it's good to sleep. This is a study from 2014 that was published in PNAS journal, and it's just a memory game. And so it is to form pairs. So this is a memory task. The children who are asked, we have the children who have napped and those who haven't napped, and we see that the percentage of correct answers is higher. If you play this and you ask them immediately, there's no difference. But in the group that napped, the difference is evident when we measure long-term memory. Do you remember such and such a thing? Or even the following day, after 24 hours, we asked them, where was that umbrella, in that task that you did? So the effect and the impact of naps would have an effect on the consolidation of memory and on the maintenance of long-term memory. Now, compared to those who do not nap, there are some children who do not nap, or some kids that the mothers don't want them to nap so that they can sleep through the night. There are some studies that have not been published yet. They have been performed in the lab of Serta Rivero, where there are some children who are really affected by napping. Their cognitive abilities and skills diminish when they nap, and they are in a refractory sort of state, and it's very hard for them to awaken. And in those children, in fact, maybe naps are not advisable, because naps, according to the study and other studies, would work in certain cases, but not in all of them. And there are certain cases in which we have to see individually if the naps are harming them or not. Here, we'll speak about the critical periods. And here we have the premature babies. I hope you don't think I'm speaking about something totally disconnected to what I was going to present. What does this whole issue of premature babies have to do with education? Well, we have performed studies analyzing the situation of premature babies. We have done an experimental analysis of this as regards to critical periods, because the critical periods underlie the issue of early education. We have to begin to educate children early because there's a time window we have to take advantage of. Otherwise, something will happen and we won't be able to learn later. That's the whole theory behind that. But what I would like to say about the critical periods is that in animals, they understood as the moments in which individuals really benefit from a stimulus and learn more easily. With a little stimulus, they achieve great efficiency. A classical example for humans is the acquisition of language, in which past a certain age, there's difficulty in learning languages as regards grammar and phonemes. And that, of course, goes to show that children learn before the age of 6. That's the time window in which they can learn very easily. And following that, they will encounter obstacles in learning. And therefore, although these critical times exist, or periods exist, they do exist, but not for all the functions. And not all of the cognitive functions depend on the critical periods. There are some activities that could be learned anywhere, even in utero, before the child is born, and they could be opened, and we could actually have individuals learn even late in their lives. Even people who are very old can learn. In this case, the model that we have is the one I will show you. The critical periods in animals, this comes from the animal world, has a biochemical regulator. Biochemically, something occurs in the brain for the brain to become especially receptive to the stimuli it's receiving. And the opening and closing of that has a biochemical cascade. This is a human brain, but you can imagine the mind of a brain of a rodent, a mouse. When you have vision, the light makes your eyes open, and there's the OTX2 transport of that to the retina of, and that makes us mature the basket cells, and those neurons are of the inhibiting type. They inhibit the region, the GABA, the GABA inhibitors, and they trigger the opening of the critical period. They open up the critical period. After that, you might say, okay, what if that critical period is open all the time? That would not work. It must be closed too. And there are other chemicals that increase in animals. We have lynx 1, which makes a sort of a network or protein begin to form in the perineural net, which is diminishes the possibility of that neuron to have multiple connections, and it diminishes the influence of those neurons. The reason I bring this up of this biochemical cascade, because it does activate the basket cells or inhibit them depending on the different neurons, and that could be modulated. In animals, it is modulated, and in the some models that perhaps have no current application, they are modulated too, particularly in animals. Through drugs, we can modulate these biochemical cascades in animals in which those critical periods have been closed. If they are blind or deaf, by administering certain drugs that allow the increase of the molecules that stimulate this, we can reopen those critical periods and offer that animal a window of opportunity once more. That by itself, if it could be performed in humans without any important side effects, would be an interesting premise contributed by neuroscience as regards the control of learning. As regards language acquisition, in language, for instance, there are certain skills in the first year of age they learn from the day they are born, and they have different perceptive acquisition of perceptive skills, phonemes, in different aspects, and they also produce different sounds that are not that linguistic. Then they begin to form vowels, and then they begin the babbling, which is the babbling of the mother tongue. The reason I bring this up is that what would happen if the child is born earlier? Because this is at month 0. What if the child is born prematurely? Would this occur earlier? This whole period, would the child begin to speak earlier? That is more or less the model we use to study whether the exposure to stimuli does trigger and open up critical periods in human beings and helps premature babies learn earlier. Well, basically, that's our model. Premature babies were born 3 months before their due date. They are all healthy. That's something important because we assessed premature babies who were born at the 6 months but had no important conditions, neither then nor now. Now they are 10 years old and nothing has happened to them throughout this whole period. The model is the following. If we have a cognitive skill, for instance, such as learning phonemes, the phonemes of the mother language, the sounds that are important in Spanish, for instance. Therefore, quote unquote, just for this purpose, I will tell you that language in the world, there are about 6,500 languages in the world, the ones that are known. There are about 600 consonants and 400 vowels, but no languages uses them all. We only use those that are distinguished in the mother tongue. And in Chile, we have 18 consonants and 18 vowels. So in the case of vowels, that occurs at the age of 6 months, and in the case of consonants, it happens a little later on between the 9 months and 12 months of age. That's what I have to learn. So supposing if that were programmed, genetically speaking, and we were to say at the age of 9 months where I have certain neural maturity, that is when I will learn. I will not be able to learn earlier, even if somebody spoke to me earlier, or because when I was in the incubator, the nurses told my mother to speak to me, then I would learn more. That's not the case. If this activity were pre-programmed, the child who's born 3 months before the due date should achieve or should be the same. For instance, here we have the pre-term and full-term babies in green, and for them to behave similarly, they would have to have the same age beginning from the expected due date. They should be maturely similar in maturity.
If not, if we compare as of the moment the baby was born, for example, after so many months after birth, the premature baby will have 3 months more. But if we assess it by growth age, at 9 months, the premature child will have a more delayed development in comparison to a full-term baby. There's a biological program saying, I will learn at such and such a date, and it will be self-corrected, so similarly mature. Not because they were born earlier will they learn earlier. However, if this is experience dependent, so if my mom talks, I learn. She's there, she's talking to me face to face every day, I could learn some things. And in that sense, stimulation would trigger the opening of these critical periods, the fact that I could learn, or rather the individual could start learning. So here would happen that the children would be similar, would have the same level of development when compared by age after the moment of birth, And the premature baby would learn earlier before than the full-term baby when comparing them according to the adjusted or the revised age. Now, that's the model. If children learn by age, or rather, if there is any skill that depends on the biology, I will have to wait until I'm sufficiently mature to learn. Now, if there is a skill that depends on experience, as soon as I'm born and I have my senses working, when stimuli comes in, I will begin learning. I will start learning earlier. So we did a study. We did several studies, but I will tell you only about this one that has to do with these words. The repertoire of phonemes. Native ones. As I said, children are born sensitive to a number of sounds that are not useful for their mother tongue. They need to learn, and this occurs after the 9 months and close to 1 year of age. And here we have a population of children that learn English and are discriminating a sound in English, and now another sound that only exists in Hindi. Here at 6 months, those English speakers discriminate everything, whereas here those that speak English discriminate only the English system but not the Hindi, similar to what happens among adults. Now, in Spanish, for example, when we're babies, we could discriminate sounds that have the vowels or the different E's in French. There are about 5 different E's, because for us, we discriminate them all as E, which does not mean that we're deaf to other sounds, because you do not necessarily have to listen to something different to perceive it differently. And so here, what we did was to compare children, full-term babies and preterm babies. They were 9 months in their mother's tummy, and here these were assessed at 12 and else at 9 months. What we wanted to see whether the babies that had been born at 6 months, after 9 months outside the mother's uterus, if they were similar to these, because what have played a role there is experience. If this one here is like this one here, it's because experience does play a role. And if the 12-month baby, after they've discriminated foreign sounds, is similar to this one here, in that case what matters here is maturity. Now, let me show you what happened. We did this with electrophysiology, and we saw that in fact what happens is that full-term or preterm babies do not speed up. It's not that they learn earlier because they were born earlier, and this is the breadth of the potential response. What I was showing you just now, based on what we do is hear the sound ba ba, and if the child makes a distinction, is seeing that br and d are different, their answer does have a certain breadth, which we can show here. This is the breadth, whether I can or not make a distinction. I need to make a distinction. When the children are small, at 9 months, either full-term or preterm, they distinguish equally, whereas when they're older, 12 months or corrected 12 months in the premature baby, the only thing that they continue to distinct is the native sound, and the non-native sound is no longer discriminated. Now, when the premature baby has achieved the level of maturity of a full-term baby, now what happens is that preterm babies do not do this language or do not learn their native sounds. There are times when stimulation could not result in learning, but it is preferable to wait until they've reached the necessary maturity. That is valid, yes, but not for all systems. For example, it is valid children do not learn either the pace of language. For example, on birth, a child discriminates different sounding languages. And more or less at 4.5 months, they're able to make a distinction of sounds that sound similar to their own. For example, when they are born, they will never notice the difference between Russian and Japanese and their own language. But that's when they're birth. But later on, they do make a distinction. If the baby is Chilean, he needs to learn how to learn Spanish. And this is not speeded up. The premature baby does not learn how to do this before. Now, so the basic language sounds, phonology, and the distinction of pace and rhythm is not sped up. But there are other things that are. It's not the fact that the baby does not respond to what is happening around them. There is a difference in the visual sharpness. Preterm babies are able to see before the full term, and also when they're faced with their mom, they learn how to interact with the baby, and the baby responds and somehow to the stimulation by the mother, and they're able to follow the gaze or whoever are looking at them. All of this is very, very important socially. Children perhaps do not know as yet, they're not prepared to specify a language, but yes, to communicate. Without verbal language, they need for someone to care for them, they need how to communicate, and social cognition, pediatrician and other signalers, they can do it. So the critical period models are not so clear-cut, because all babies do the same. No, these cycles occur at later stages as well, and not necessarily are there skills that simply do not have a critical period that totally depend on experience. What we have here is our model. For example, the basic language units do have here a very specific period that does not vary too much with upfront stimulation based on our premature model. And visual cognition and sound cognition are brought forward, and they have the same effect of benzodiazepine or valproic acid in the animal models. Yes, when they're given valproic acid or benzodiazepine, learning is brought forward. Now, there's also the possibility here of reopening with the use of certain drugs at these critical periods. And what's the point of all this? Another thing that neuroscience is saying, well, it helps us to understand how children learn, have an idea of models, and how these models could now or in future serve as the grounds for some type of intervention. So another study is when we see, well, what happens with sensory expertise or possible expertise that children gain and have a predictive value. This is a study done by Leppänen in Finland that involved 1,000 children, and there was follow-up. These are families that had a history of dyslexia, and they had evoked potential similar to those here, as Rosario was saying. And you say, it's the same sort of phenomenon as these sounds, as mentioned earlier. And as you see, these children did not have reading problems and had a fairly nice evoked potential here. And then you had the others that come from families with dyslexia, and they did have a reduced evoked potential. But now, as newly born children, these babies are 1 or 2 days old, and these were followed up on until they joined school. And at school, they found that this breadth that the evoked potential had, especially in this F4, predicts the reading and writing skills in 2nd grade. So if we could take these children and have a standard and say, look, I detect that this child reacts well and this one for some reason or other does not, so we could predict that at school they will have difficulties in reading the speed of reading, and also spelling. Now, let me give you another example, reading. Reading, I like this very much because this is an area that has been studied in various levels of complexity. There's a lot of data in relation to reading from neurosciences showing how you learn how to read. People who are not deaf, they use language to begin reading. And what are the centers involved in reading? Well, initially, those that you use to learn how to speak. And then you add other components that have to do with vision and representation of these letters. Basically, this model by Ghislain Dian, recently, what we added was this. This is language. These are the linguistic networks. Here I could see, say, indefinite hypovisuals, and what happens is that when you begin reading, we develop special areas that will exist as the areas of letters, for example, where you represent, well, since we are expert in letters, so this is a region that is activated with expertise, and this interacts with the other networks that have to do with language. Now, this is what changes. There are different activations. A 9-year-old child that already knows how to read, whereas another of 6 that does not read so much. And there are areas that are among those beginning to read, and others that don't read at all. They just know a few letters, but they don't really know how to read. There are differences in the brain organization. There is a brain plasticity, which happens in normal children, but also there are reading difficulties. And neuroscience models have been quite good in order to specify that there is a lot of work here. I just selected a few to show which would be the neurological or neurobiological disorders of these reading difficulties. Let me put to you the case of the brain cortex. When you do not have consolidated dyslexia, there's a reduction of gray matter in these areas. This is the left and this is the right hemisphere, and here you have the posterior part. And also there is a reduction in activation. These areas, not only do they have less gray matter, but also they're activated less when children or adults must read. And also at histological level, if you remember, this is a drawing I was showing you earlier, and the various levels where neuroscience would like to understand everything. But here we have the level of cortex, and here we have another histological level. There is work done by many authors, but I would also like to add Bedelaruna, the Chilean. He was involved in the first discoveries in that there are certain ectopy phenomena, which means to say that a neuron that should be over here goes over there and ends up somewhere where it should not be. And that is quite frequent. Although not specific to dyslexia, it is frequently observed in children and people who develop dyslexia. And this change occurs early on. Neuronal migration occurs in the second semester of pregnancy. And as a baby, you could be already identifying this at that age, risk factors in reading in subsequent stages.
Another one is dyslexia and also temporal processing. In reading, we need a temporal integration because the eyes move in time, and I need to integrate what I see and transform it into the sounds, those who have good hearing, and not to forget what we have read so we can understand the whole text. That requires temporal integration that is quite essential. And in this case, I will highlight 2 systems that have been detected in dyslexia for temporal processing. One is the magnocellular system that has to do with the perception of movement, of fast movements that occur at the visual level, and also the magnocellular auditory phenomena. For instance, in this case, if we have the problem in the magnocells, here we're comparing the histological aspects of the cells. Here we have the abnormal magnocells in dyslexic children, a normal child and one with a child with dyslexia. At the temporary processing level, something that's difficult to do is to try to integrate information in time. We must be able to follow. For instance, if we believe that the reading is based on our capacity to perceive speech, then we must be able to follow someone who's speaking. If I speak very fast, you must be able to follow what I do and integrate what I say in time, different units in time. I am using phonemes, which are here, for instance, you have different events occurring when I'm really fast and I'm speaking at full speed. There are maybe 20 phonemes per second could exist in a sentence, and there are syllables that occur every about 4 syllables per sentence, and then we have stress and intonation, and whether I'm asking a question or I'm stressing certain parts of the words or sentences. So I must be able to integrate all of this information to be able to physically process and trace all of this information, all of these units, to be able to extract information from them and understand the message. In people who suffer from dyslexia, this activity is diminished. This oscillatory activity of 30 hertz. For instance, people follow the syllables, follow the intonation, and they can do na 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 na, but when things begin to go quickly, they get lost. And that's where we have a problem with the sampling and the number of things that I'm able to process in time. This is something that we perform too. Basically, the skill to be able to follow a stimulus, for instance, you begin with responding. Parts of your brain that has to respond to this, following the syllables. And you must also be able, or your brain must be able to follow words. And this activity, this capacity to resonate and follow the stimuli that come from speech occur already in 3-month-old babies and in premature babies, preterm babies. So neuroscience tells us a little bit how we process the stimuli that will later have an impact on how we learn different contents. And here we have connectivity. The phonological conscience might be compromised. It's not that I don't distinguish a P from a B. It's rather a problem of connectivity between or among all the systems that are involved. For instance, children with dyslexia have a less volume in this area of the brain, which you can see that I'm pointing at. There are connections that exist between the centers that are called Wernicke and Brocadt. Finally, I have 1 minute left, 5 minutes left. Okay, 5 minutes left. Finally, we have dyslexia. For instance, another component here that is genetic, and that's a show. For instance, this is not a human model, but it does show in rats that there are some genes. When we look at the molecular aspects, there are problems in the region, in the area of the brain, or there are problems at the level of the histological organization and connectivity of the neural networks that could have these genetic components like FOXP2, which has to do with speech, or others that have to do with reading, for instance, a rat reading. I mean, that's not exactly something that could be replicated in a child, but we do have an animal model of what could be the representation of the link between sounds and written letters. Another important aspect is that although there's a lot of issues with dyslexia and things that we could help, for instance, here neuroscience shows the impact of remediation. For instance, in the case of a child with dyslexia, that is typical. No, this is a typical reading child. This is a child with dyslexia, no treatment. And this is a child with dyslexia after remediation. So there is an impact that can also be assessed by means of neuroscientific methods. So neuroscience can help us understand why the phenomena occur and why the things are happening the way they are or how they are working in the case of remedial therapies. And this also allows us to act at a cultural level. Dyslexia is not the same in different languages. In English, there's a lot of dyslexia. The phonology is not transparent either, and there are many ways of writing E in English. You probably know this better than I do, but E can be spelled differently, whereas in Spanish there's a one-to-one correlation. There's only one way to spell I and Y, for instance. So that makes dyslexia more frequent in French and English compared to Italian and Spanish, which are more phonetic, so to speak. There's more transparency between the sounds and the letters that represent those sounds. So there's a cultural component. And neuroscience could help us understand why we could use, or why a child, for instance, that has difficulty reading could learn a second language and not be dyslexic, for instance, to do individual interventions. So the model of dyslexia involves findings occurring at different levels, and that's what we're trying to apply for everything. We wish we had a model like that for everything, for mathematics, for geography, or for any type of learning that goes on in the classroom. This is another example of how the numbers are processed in the left hemisphere and the right hemisphere. And this is based on a vast number of findings from experimental trials that have been performed since the 1990s. And these are the conclusions that I wanted to arrive at. First of all, I do believe that neuroscience can, in fact, contribute to education. Maybe it's not as clear as the connection with medicine, for instance, or business, where neuroeconomics has been quite accepted. In education, there's a possibility to continue progressing. I think that basically neuroscience helps us why and how, or what, for instance, what children learn, at what ages they learn it, and under what circumstances, and using what pedagogical or teaching strategies, and how we can achieve good or bad learning. Sometimes we cannot make a direct cause and effect type of connection, and we can't say that neuroscience can explain everything. There are different reasons for all the examples that I gave you. There are different revisions that have been performed, and there are some comments against them saying this works, but it does not work in such and such a circumstance. So that is something we need to live with. Neuroscience is merely one more tool that is connected to biology, but not because of that relationship with biology does it become more accurate. And it's sensitive to individual variability. And here, for parents, professors, and politicians, we wish them to look at this with a critical spirit, because there's a myth about neuroscience in that neuroscience will solve everything, but that's not the case. We cannot do that. We can issue recommendations on specific points, but on many points, we have no validated recommendations. Validations should hopefully be be based on proven facts. I will say something that might be a bit political. When you want to apply a vaccine in medicine, first you vaccinate the rats, and then you do the monkeys, and then some children, and then when you see that nothing has gone wrong, you vaccinate the whole population. So the idea with the reforms, educational reforms, or reforms based on neuroscience, is that we should apply caution. Say, okay, we have tried this on rats at the lab, let's see what happens in a small school setting, and then if they work and they can be optimized and they could be spread out to the whole school population. We must also think of the message. Teachers are, of course, behind this whole process, though they are the ones who are very important in this process. Here, research has been based, for instance, in Chile, on intuition in, and also lab sort of findings. But here, we would need to hear the opinions of those people who work in the classrooms and people who are involved directly with the educational process. This is something we must be cautious about. This is myth. Music helps learning, like the Mozart effect. It's proven that it's not, that we use 10% of the brain. If everyone has seen that movie, Lucy, it's the tearjerker. But what we show here is that we have left and right kind of hemispheres of the brain. Instead of speaking of left and right, we should think of the whole brain. Some people are better at reading because they listen to Mozart early on. That does not exist. We do not make that kind of assertion. You can find that in the newspapers, but what I would say is be cautious. Don't believe everything you read in the papers. Look for second opinions and look for other opinions, and also the reality, how neuroscience can help. It can explain about the plasticity, neuroplasticity, and some impacts and strategies of pedagogical type. Something else, I have a minute left. Some people say, okay, neuroscience is not useful for anything. John Brewer, who has funded a school that we have, he's a marvelous person, very open-minded. However, despite he finances our school as neuroscience and education, he says that education is good for nothing and neuroscience is good for nothing. He thinks because it cannot give you useful information for a teacher in the classroom. But I think that if, for instance, learning that the prefrontal cortex activates when I'm doing a task is important and interesting when you understand how. But how is that useful to a teacher in the classroom? Teachers cannot see the prefrontal cortex of children. It's not something that you can flash a light on, or and measure it and say, oh, this cortex is bigger than another one. So that part is something essential. But what John Brewer says is that it may be very relevant to see that parietal and prefrontal regions are keynotes for number processing, but this does not seem to help a teacher teach math. So maybe the result will not be a bridge. It's not just one single bridge. We need a whole system of bridges. We need those connections to be, for instance, some more robust than others, some smaller than others, with different associations. There will be people who will go down one bridge and another, and there will be great individual characteristics. But it could also be as confusing as this other image here. Maybe those bridges do not follow the logic that we are asserting it they do, and we must be a bit more creative and have more opportunities about applying what we have in situations which do not necessarily adhere to these experimental paradigms that we are working on right now. Two more. Do I have time to show you two more? Please allow me. I like this because it says, who says that everything's lost, that all has been lost? Because I'm always invited to speak about neuroscience and education, and I always say, no, you need to be cautious, maybe it's not good for anything. Well, that's what happened to many people. I like to give this example of DNA. In 1920, scientists thought that DNA was a too simple molecule to have an important role in genes and inheritance. In 1953, they found the secret of life. People tried to look for the secret of life and how we could manipulate all this. Many questions emerged, and people got together and began working on this issue. And around 2000, there was the first draft of human genome, and many applications emerged. For society, that very small molecule, no one knew what it was good for, currently has applications in domains such as distance as law, the law of inheritance, for instance. So it does show that this is possible. It is possible for us. Maybe in 50 years, 200 years, but somehow the collaborative studies in this area I think are worthwhile promoting because they will in fact help us understand how children learn and understand that neuroscience does have a role in this whole story. Finally, we'll show you this. Can you please move on to the next one? This is a study I would like to show you just to finish. Can you please click on the video to make it run? There should be a sound to this. This is a young girl trying to learn how to read. No, it doesn't. The video is not playing all that well. But this is the passion that drives our work. That passion of finding out what happened in that girl's brain. I think the brain has a lot to say in this aspect, and I think it's worthwhile to make the effort. Those are the people who participate in our study. There's Camilo, who works with math, Severino in reading, and Pablo Barraza. The three of them I would like to highlight because they have a passion for education. That would be all.